All right, so welcome to our lecture on plate tectonics. Plate tectonics is so exciting, and it's something so bigger, so much bigger than us as well, and daunting to think that all of these actions are happening on the world in such a grand scale, the world and the earth that we actually live and move and breathe and create our lives on. So, what you're looking at here is a photo of the San Andreas Fault. Now, in many places where we live in Southern California and California, you can't actually see the San Andreas Fault like this. You don't notice it as much. But in an aerial shot on the Carrizo Plain in Central California, this is where you can really visualize what the San Andreas Fault looks like. So the San Andreas Fault is a fault line, and it's the most major fault line that we have in the Western United States in a continental space, but it also forms the boundary between the North American plate and the Pacific plate. So the majority of Southern Californians actually live on a separate plate from the rest of Americans if they're not Hawaiian. Most Americans live on the North American plate, and most Southern Californians, if you live on the west side of the San Bernardino or San Gabriel Mountains, live on the Pacific plate, so a plate that is shared with the Pacific Ocean and the state of Hawaii. It's massive. All right, so in order to understand plate tectonics first, we need to understand what the topography of the Earth looks like. And this is a really beautiful image of if you would scan the top of the Earth, what it looks like. And in particular, this area we're talking about is in and around some of the volcanic mountain range in Oregon and the state of Washington. And that mountain range is called the Cascade Range. It's a volcanic mountain range and it starts in Northern California and actually ends in California, Southern Canada. And topography stands for the major surface features of the Earth's crust. And the reason why we've chosen this photo is because we're looking at volcanoes. And I happen to think that volcanoes are a lot of fun. So, in continuing our conversation about the topography of the Earth, we have relief features of the continents. Those are like landforms. Relief features means anything that comes from ground zero and moves up from zero. So, anything of any sort of elevation. Obviously, in the Western United States, we're used to lots of relief features like hills, mountains, cliffs, and valleys. Relief features of the continents include what we call alpine chains, which basically means mountain chains, volcanoes. An example of that is the Cascade Range. That's the nearest one we have active to us. The nearest volcano we have in Southern California is Mount Shasta, which is in Northern California, just about an hour drive away from the Oregon border. And relief features also include landforms that have come as a result of tectonic activity, which is what we consider plate tectonics, the movement of plates. Example of that is the Himalayan range, which we'll be going over in just a minute. Another example of some relief features of the continents are what we call continental shields. There are the basically the remnants or the leftovers from what used to be large mountain or large alpine chains that, or in the last ice age, were overrun by glaciers or glaciers, as they call them in Ireland, where I was trained. And these continental shields are very, very old. We're talking hundreds of thousands of years old. Also, we consider relief features of the continents to be the roots of old mountains. So, a great example of the roots of old mountains are the mountains in the eastern United States, and those are called the Appalachians or the Blue Ridge Mountains. Those are very, very old mountains, and they're considered now actually a mountain root. So, what used to be very tall very young mountains have now been out and exposed in the Earth's surface for many hundreds of thousands of years. And here is a photo of what they would look like on the ground if you ever go to, for example, eastern Tennessee, eastern Kentucky, Western Virginia, Western North Carolina, certain parts of New York, and also Pennsylvania. And I'm pretty sure I'm missing a state in there. You'll notice that they start here and they run all the way up to this is Pennsylvania, Western Virginia, Virginia. This is Kentucky, Tennessee. Oh, and you've got a little bit here in Georgia and Alabama, your South Carolina, North Carolina. And this is New York. Another example, this is what we call the Canadian Shield. So when you go there, it looks very similar to this photo that you're looking at here. When you're flying over it, it looks like this. And yes, I am that person who takes photos out of a plane window. Basically, the evidence of just very, very old mountains that now are kind of like a shield, just like a nice rocky shield that sits over the Earth's crust, like a protective layer. Other items that we have that are considered relief features of the continents are widely spaced mountains, like we have in Nevada. It's considered basin and range. Ice sheets that we have that are so heavy and so vast that they actually have they're responsible for sinking the continent of Greenland underneath the ocean. Plains that we have represented here in the middle of the United States. Very sharp and very young mountains like we have in the state of California, the Sierra Nevadas. We have depressions. Those are considered relief features. We have high plateaus. Plateaus are considered flat spaces that are at high elevations. For example, the Altiplano and the Andes Mountains in Peru and Bolivia. This is what you're looking at here. The average height of these plains are at 12,000 feet. That's extremely high. Other relief features that we have on the continent are also things that we have in the ocean basins as well. So you'll notice that even in the ocean basins, we have ridges that are covered by millions of gallons of water, and we also have trenches. The deepest of trenches in the world is the Marianas Trench down in the oceanic crust. It's so deep that we're not even able to, as humans, create a submersible or some type of remote device that can even go down into the depths of the Marianas Trench. So here we have created things to visit the moon and visit Mars, and we have yet to create something that can actually go down to the bottom of the lowest trench in our own oceans. And when we're talking about tectonic plates, what we're talking about here is this is a satellite image of what the ocean basins look like. So here you'll see here's the eastern side of the United States, the Caribbean, and here's South America. So what you're looking at is the bottom of the Atlantic Ocean and what that looks like. And you'll notice this sort of etched line here that goes all the way through. And then we come into the island nation of Iceland here, which we're going to be talking about in a minute. Here we have another image of undersea topography, and what we're looking at is the Pacific Ocean over in the eastern side of the Pacific Ocean. Here you're looking at, here is the country of Japan, which was created by volcanoes. Japan is considered what we call a volcanic arc created by volcanoes. Those volcanoes were created by this subduction zone that you're noticing here. And we're going to talk about that in just a minute. So, where did the idea of plate tectonics originate from? Now, many hundreds of years ago, we didn't even realize that this was a thing until we started recognizing that the way that Africa as a continent fits into the continent of South America, it almost looks like they used to be puzzle pieces that fit into one another. The other thing that people started to discover is that we noticed there were similar mountain ranges with the same rocks here in South America and here in Africa. We also noticed that these same mountain chains started here in the eastern United States and extended up and through Canada and into Europe. Same rocks. Not only that, but biologists started to discover that there were similar plants and animals that also lived in conjunction with each other on either side of these continents. And so we came to the conclusion that there was this theory of continental drift, and that's how the idea of plate tectonics originated. The other item that they discovered was that in the middle of the oceans, we had these ridges. And we call this the theory of seafloor spreading. So remember that image that I showed you of the Mid Atlantic Ridge that is a line that goes all the way through the middle of the Atlantic Ocean. People started studying the rocks on either side of that ridge. And they said, oh my gosh, that's really interesting. They're the same rocks on either side of this ridge, same polarity. And then they started measuring the rocks even further on either side of these ridges. And they started to recognize that the rocks on either side of the ridge were the same age. And so they decided that this idea of seafloor spreading was occurring. That in the middle of this ridge, material from the asthenosphere was rising, hardening, creating new oceanic crust, and then it continued to move. And then was created a history of the continents. So, what you'll notice is that our continents are not static, our continents move. Now, for us as humans, our lifespan in comparison to the Earth's geologic time is very short, like that almost of a fly. So, for us, the idea of continents moving really isn't that significant when we think that in the last earthquake, Japan moved 6 feet. And that's really considered in geologic time pretty significant. But what we had here is 200 million years ago, the continents look as though they were one giant megacontinent. And we call that term Pangea. So 100 million years ago, here's what the formation of the continents would have looked like. And 50 million years ago, and here's present day. We also have projections as to what the continents will look like 100,000 years from now, and then 5 million years from now, 10 million years from now, and our continents continue to move and change. So herein lies the theory of plate tectonics, which is a theory that the Earth's crust, the lithosphere, is divided into 12 major plates, and they're all moving in different directions. This plate motion causes them to either collide, pull apart, or scrape past one another, and we're going to go over those in just a minute. Each type of these interaction causes characteristics of the Earth's structures and creates different landforms throughout the Earth. And this word tectonic refers to the deformation of the crust as a consequence of how plates interact. And we're going to go over all of this. So here is an overall view of the world plates. So here is how the lithospheric crust is divided. It's divided into the plates that you're looking at here. So as I said at the beginning of the lecture, Southern Californians actually live on this Pacific plate, while most Americans live on the North American plate. So, what are these plates made up of? Now, in our previous lecture, we talked about the lithosphere and the asthenosphere, right? The lithosphere is known to be brittle and hard, and that is considered the Earth's crust. The asthenosphere is hot and malleable, so think of red hot magma. So the plates are made up of the rigid lithosphere. So what you're looking at here. The lithosphere is made up of the Earth's crust and this layer here of the upper mantle. Now, below the lithosphere, we have the asthenosphere. And remember, astheno is the Greek word for able to move. So when we get to the mantle, this is the part of the asthenosphere. The asthenosphere is heated up, it's hot, and it moves. Doesn't move quickly, but it moves. And the lithosphere, since it's hard and brittle, moves and is dragged along when the asthenosphere moves. So, for example, the Earth's inner core generates a lot of energy. That energy heats up these convection cells. So if you've ever boiled water before, you need an energy source, right? You either need electricity or you heat up with gas. Then your water boils. What happens when your water boils? It rises to the top, doesn't it? And then what happens to the water? It rises to the top, it boils, and it either condenses out and into steam and becomes a gas, or the water moves to the sides and goes back down again to be reheated. That's exactly what's happening in these convection cells. The mantle is heated up by the Earth's inner core, rises because heat rises, and if there are no places for it to exit in the Earth's crust, which there are, right? Like hot springs, like volcanoes, it drags along, it heats up, and then it moves again and goes back down to become reheated again. As it does that, it takes the lithospheric plates with it. And that's why the lithosphere moves. That's why our continents move. So here is another image of the ocean crust and plates that are actually colliding as a result of being moved by this amazing force of the asthenosphere being heated up, moving, and the lithosphere being dragged along with it. Here is another image of these convection currents. They're extremely important as they are the driving force behind plate tectonics. Is in this example, you will notice that they have the mantle rising into an oceanic ridge, like we were seeing in our previous example, with seafloor spreading. So, this liquid hot mantle in the asthenosphere rises, surfaces, cools, becomes rock, and that doesn't become rock continues along its pathway to come back down and be reheated again. And as it moves in its convection current, this outer layer of the lithosphere, right, is moved along with it. Now, as that happens, sometimes plates will collide, sometimes plates will pull apart, and we're going to talk about those implications in just a minute. Here is a video for you to watch.
Convection is the heating and cooling of the mantle. The hot mantle rises towards the crust, where it is then cooled, causing it to sink back down to be reheated. And this cycle is repeated and moves the plates along. Anywhere two plates meet is called a plate boundary. There are three main types: convergent boundaries, divergent boundaries, and transform boundaries. I'll talk about each of these briefly.
Now, this is exactly the next
Thanks
step
for stopping by.
that we're going to be taking. Now that we've learned about the convection cells and how they're responsible for being the driving force in plate tectonics, we take a new look at these plates. Now, we're looking at these plates the same way we did in our last map, but with an added twist. Now we're looking at them in terms of their plate boundaries. Why do we care about the plate boundaries? Because remember, at each plate boundary, there are going to be different things happening. So either when you have two plates that meet, like for example, here at these borders, or here down in Southern California, or here in the ocean outside of Japan, plates are going to do one of two of three things. They're either going to be pulling away from one another, they're either going to be colliding and moving toward one another, or they're going to be slipping past one another. And you'll see that those plate boundary interactions are indicated in this map. So you have a convergent plate boundary, here represented with little teeth. Convergent means that's the location where plates interact and move together, so they collide. They're collision zones. The part of this legend is going to indicate a transform boundary, so a very simple light sort of pink red line. A transform boundary is a plate boundary in which two plates meet, but they don't collide or they don't pull apart. They slip past one another, and that's what the San Andreas fault represents. The other sort of plate boundary that we have is an example where when two plates meet, they're actually pulling apart from one another, and we call those divergent boundaries. Divergent meaning pulling apart or pulling away from one another. Now, we're going to take a look at the topography of the Earth in a new light. We are going to notice a correlation between the location of landforms, major Earth's major landforms, and our plate boundaries. So if we go back and look at where our plate boundaries are, you'll notice that there's a plate boundary here in the western United States. There's also a plate boundary here in the western part of South America. Now let's move again and take a look at the topography of the Earth and notice for Earth's landforms. You'll notice that many of the relief features we have in the western United States are here as a result of the fact that we have a plate boundary right here in the western United States. And you'll also notice that we have a plate boundary here in South America as a result of that plate boundary that we saw in the previous map. Here is another beautiful example of these plates with their associated names. Here is another beautiful image of what the lithosphere might look like underneath a mountain chain. It's a little bit thicker. And to remind us that the lithosphere is a word that stands for rigid and is made up of the crust and the upper part of the mantle. The asthenosphere is distortable, and it's weak. Here is another image to remind us of the importance of the convection cells. Here is another image of those plate boundaries and a reminder of how seafloor spreading and plate boundary movement works. This brings us to going over the different types of our plate boundaries, and we have three of them, as previously discussed. When plates meet, they do one of three things. They either pull apart, which is indicated here in divergent plate boundary interactions. They converge, which means they compress or they collide, or they move past one another, and we call those transform plate boundaries. Now, when plates move together or when they converge, they are going to do one of three things. So, in these convergent plate boundaries, we're going to have different types of crust. And on Earth, we have two different types of crust. We have oceanic crust and we have continental crust, and they're all going to behave a little bit differently. So, in these convergent plate boundaries, if you have continental plate that is crashing or colliding or converging with another continental plate, it's going to make mountains. And the greatest example we have of that on Earth are the Himalayan mountains. The Indian plate, we'll go back to this and I'll show you. This plate here that the nation of India and Pakistan are on form its own plate. This plate moved north and collided with another continental plate, and as they collided, they built mountains, the tallest mountains on the earth, known as the Himalayas. These convergent boundaries are also associated with collision zones where oceanic crust meets continental crust. And when in this image here, you'll notice that when oceanic crust meets continental crust, every single time, the continental crust is going to win. That means that when a oceanic crust collides or converges with continental crust, the oceanic crust is always going to subduct or go underneath the continental crust. And those we call subduction zones. It's the place where the lithospheric plate of one plate dives back down into the asthenosphere. And you're right, goes into the asthenosphere, becomes reheated in the upper and middle mantle, and becomes part of the asthenosphere again. And this is what continues the cycle that we know as the rock cycle. We also have convergent plate boundaries where oceanic crust meets oceanic crust. And in those examples, one plate will go underneath another one, and that will create areas of volcanic activity responsible for the creation of the Japanese island nation. And they will create trenches. The trench which we looked at in a previous slide, known as the Marianas Trench, a trench that as humans we have not even been able to get there, even using electronics or building some sort of a device. Another example of a convergent plate boundary that we have nearest to us is actually the Cascade Mountain Range that we discussed earlier in the beginning of this lecture. The Cascade Mountain Range is created by an oceanic plate off the coast of Northern California, Oregon, Washington, and southern Canada, and it subducts underneath the continental North American plate, becomes reheated, and resurfaces again to create volcanoes. And I'm going to show you what this looks like. So, off the coast of Northern California, Oregon, and Washington is an oceanic plate called Juan de Fuca. And it is a subduction zone, it is a collision zone, it is a convergent plate boundary where you have an oceanic plate colliding with a continental plate. It subducts, creates a subduction zone, and this oceanic plate now rejoins the asthenosphere, becomes reheated, and surfaces to create the Cascade Volcanic Mountain Range. Those volcanoes include volcanoes such as Mount St. Helens that erupted in 1980, Mount Rainier close to Seattle, and Mount Shasta in Northern California. Here is an image of that plate here, the Juan de Fuca plate, and is responsible for the creation of this volcanic mountain range known as the Cascades. So here you have the Juan de Fuca plate, which is an oceanic plate colliding with the North American plate, which is a continental plate, subducting and responsible for mountains and volcanoes. Here's another video. This one's being a little tricky. Well, hopefully, it will allow you to play on your own. Here we go. Go to earthquake, tsunami. All right, I'm glad that finally worked. Another great example that we have of a convergent plate boundary, oceanic meeting oceanic, is Japan. You will notice that Japan was created in what we call a volcanic island arc. And you'll see that it begins like this, where you have an oceanic plate diving and subducting underneath another oceanic plate and creating volcanic activity. This volcanic activity takes matter, right? Heats it up, resurfaces it, and as it cools, it becomes land. That land is now, over millions of years, become the island nation of Japan. You will also notice that there is a pattern between, if you look at the all of the maps that we have throughout this lecture, of the border of all of the plate boundaries of the Pacific plate, and then line them up with the amount of volcanoes and earthquakes. The highest amount of volcanoes and earthquakes that we have on planet Earth are in an area of what we consider the Pacific Ring of Fire. We call it that because the Pacific plate, not the Pacific island, not Pacific Islands or Pacific Ocean, are associated with subduction zones. Subduction zones are associated with earthquakes and volcanoes, and that's where we get the Ring of Fire. Fire known for fire created by volcanoes. So, again, in review, our convergent plate boundaries are areas of collision where plates collide, and they do so in three ways: where it's oceanic versus continental, and oceanic will always go underneath the continent; oceanic versus oceanic, which will create an island arc or a trench, like Japan or the Marianas Trench; and oceanic versus continental, it creates a volcanic mountain range, and we have an example of that in the Pacific Northwest, up in Oregon with the Cascade Mountain Range. And in continental versus continental, when two continental plates collide, we have an example of the Himalayan mountains. Here's another example of what that looks like. The Himalayan range is continental versus continental in active mountain building. It's a convergent plate boundary or a collision zone. 71 million years ago, the subcontinent of India was considered its own continent, and over time it moved. And as it did, it collided with the Eurasian plate, creating what you're looking at right here are the highest mountains currently on planet Earth. And I charge you to find where the Himalayas are and see what type of plate boundary you will find. Here is that image again that we saw at the beginning of our lecture with regard to what these plate boundaries look like on the ocean floor if we were to take away all of the water. So here again we have the mid-oceanic ridge, which is a ridge of oceanic plates that are pulling apart from each other. We call that a divergent plate boundary. Here is a convergent plate boundary of oceanic versus oceanic in the Pacific region and responsible for the creation of the island nation of Japan. Another example that we have of a diverging plate boundary or plate boundaries that are pulling apart are two: the island nation of Iceland and the East African Rift Zone. So we're talking about plates that are pulling apart now from one another, not colliding. So the examples that we have of lithospheric plates that are diverging or pulling apart from one another, here's an image of Iceland and what it looks like from the air. So initially what starts to happen is that you can have a rift in an ocean, you can have a rift or two plate boundaries that are pulling apart from one another either at the oceanic level or it could be continental level. Over millions of years, this continent is going to pull apart and become so thin that it will eventually thin out so much that it will allow water in. So, lakes, rivers, and eventually seas and oceans. And we see an example of that in the Red Sea in the East African Rift Zone. And I'm going to show you an example of that in just a minute. So here is what this divergent, the Mid-Atlantic Ridge divergent plate boundary, where you have two different plates that are literally ripping or pulling apart from one another. And they do this through the middle of the Atlantic Ocean, but they also do this as well in the middle of the continent, an island that we know of as Iceland. These are little people here represented in this image. This is an image from Iceland's Rift Valley, where the continents of America and Europe are drifting apart. One of the reasons why Iceland also has volcanoes, they have active warm springs, and Iceland, the entire nation, is run on geothermal energy. Here's an example of what the Mid Atlantic Ridge looks like running through the middle of Iceland and also through the middle of the Atlantic Ocean. Here it is as well. We also have a divergent plate boundary in what we call the East African Rift Valley. So, this divergent plate boundary goes through the Red Sea and it also goes in and around the Arabian Plate. You will notice that this also is resulting in the continental thinning and diverging of the East African Rift Zone. So these two plates are actively pulling apart from one another. Now, the Arabian Peninsula here and this part of Africa actually used to be joined. But because those two plates have been pulling apart from one another for millions of years, it thinned this continent and then became so thin that it allowed in, as you will see here, more rivers and lakes because it's just going to hold water. There's nowhere for that water to go. And then eventually, what will happen is the sea will come in, as it did here for the Red Sea. And here is an example of the continent of Africa where this Great Rift Valley is occurring and where Africa is actively pulling apart from itself. This Rift Valley is created here, and it also created the Red Sea. You will notice this is a satellite image of the Red Sea here. And you can honestly see this is the East African Rift Zone. You can see how this land from satellite image is just being ripped apart. It's just being pulled apart. So this is a modern day example of continental plates pulling apart from one another, creating depressions. We call this the Afar Depression. So it's the thinning of continental crust. And pretty soon, as you will see how it's thinning here, it's going to open the way for the water from the Indian Ocean, from the Red Sea to come in. The last example we have of a plate boundary is called a transform plate boundary. So a transform plate boundary is a boundary in which plates are actually slipping past one another. The greatest example we have of this is the San Andreas Fault. And here you will notice this is the western United States. This is California. Here's LA. Here's San Francisco. The San Andreas Fault goes right through the city of San Francisco. The San Andreas Fault runs through like the Palm Springs, Coachella area and up actually behind the San Bernardino and San Gabriel Mountains. And I'll show you an example of that in just a minute. The San Andreas Fault is also responsible for creating associated faults. So, faults that run off of the San Andreas Fault are also the Inglewood Fault that runs from Inglewood down to Newport Beach, and the Palos Verdes Fault, which is responsible for creating the peninsula of Palos Verdes. Here is a video of how transform faults work. Here you will notice here is the transform fault represented here, and it's going to show you in just a moment how transform fault boundaries represent a location where plates are actively slipping past one another, as represented here in the San Andreas Fault Zone in California. Here is also a map of Southern California. Here are some of the faults that we have in California. Back here, this is the San Andreas Fault, so this is the main fault. And off of this main fault, we have associated faults. For example, we have the Plana Hills Fault, we have one in Pasadena, we have one in Whittier, we've got the Whittier Fault. The Newport Inglewood runs here and down, and the PV Fault is down here. Here is actually a route if you would ever like to follow it, and this will take you up to the Carrizo Plain where you can actively see the San Andreas Fault. But here you can follow along the San Andreas Fault as it travels back behind the San Gabriel Mountains. So once you have driven from, let's say, Rancho Cucamonga or Pasadena up into, let's say, Hesperia or Apple Valley or Lancaster, you have driven over a plate boundary from the Pacific Plate to the North American Plate. And finally, we finish with this beautiful photo, an image and map of all of the Earth's plates associated with how the plates interact with one another, including earthquakes and volcanoes, which will be where we pick up in our next lecture.